before, but that's okay. Recorded. A good example is this one. There was some number in the numerator, I don't remember, maybe 3. 1 plus e to the k. You can solve that by the ratio test. I think you would have to use L'Hopital's rule at some point along the way, but you could do it. It's not the one I would think of. Instead, I would think of, just the nice geometric. You know that I love geometric series. And so I would just toss the 1 out and look at this geometric series. And you can write it like this. That's the value of r. It's less than 1. It converges. So that seemed to be like the best one. You could also use the integral test. It would surprise me with, again, this is my end of my 41st year of teaching full-time. I don't know how many students I have that could solve that by the integral test, but it's possible. And so if you wrote it down, I didn't tell you you had to run the test. There were a few people who did run the test and made bad mistakes. And so, that kind of costs you a little bit. On this very problem, there are a few, I'm going to assume this is test anxiety, like you really know better than this. And maybe I wrote something like not all that flattering on your paper. Like, they wrote this, I'm like, oh my goodness. Never ever can we do that. That's just bad algebra, right? And like I said, I'm going to assume you know better and just test anxiety that led you to it. It certainly makes the problem easy, so I don't blame you, for trying to find an easy way to go. But, a wrong way to go is not a good way to go. All right. If you have any questions, Matthew already asked me one, but probably better if you came to me outside of class and let me know what your question is. As always, check my arithmetic. Make sure the scores add up. Remember that there is a one problem didn't count in your grade. There's actually this is interesting. I'm not sure it's good, but the grade distribution was flat, like 5 A's, 4 B's, 4 C's, 4 D's, 4 F's, something like that. Virtually identical. There were 2 hundreds. One of them was 100 even before I discounted the problem. Like somebody got 116 out of 116. I'm talking about both of my classes here to get that distribution of scores. Another one, I think, didn't try very hard on one problem because the student felt like they got the other 4 nailed, and so they didn't need to worry so much about the extra one. The scale sort of spread out a little bit, unfortunately. And it can't go above 100, so the spread meant it went a little bit lower. Anyway, go over the exam, check out the videos. Today is one of the best learning experiences of the semester for most of you, because on Wednesday, I put the test in front of you and said, go for it. And it became obvious for most of you, like, these are the things I don't know how to do. I wish I did, but now's the chance. And so, in real life, we say we learn from our mistakes. And so this is a chance for us to do it. And it's up to you. Like, you got to dig in, you got to do it. And we're going to still be working with infinite series. So there's reason for the next material and also for the final exam. There's certainly reasons for you to not give up, make the progress you can make in understanding infinite series. Anybody have a question for me? The only exam left is the final exam. I haven't looked at the final exam schedule yet. One of these days we'll identify when that is. I typically allow students to take the final with, if I have more than one section with either section, I have 2, so I'll let you know both of those times, when we need to. We have 2 weeks left before finals, and next week we lose Wednesday, right? It's a day of rest, quote. One of the days we didn't get over spring break, maybe. So that gives us 5 class, well, 6 counting today, 6 class periods. We have a little bit to do in the chapter we're currently in. And then we have a couple of things to do. Once we finish, we probably will finish on Monday. And then the last thing we do is totally different. Like we're done with infinite series. They'll be on the final exam, but as far as what we do in class, we're moving on to very different topics. All right, I think this is in section 3. It's called Taylor and Maclaurin series. Taylor and Maclaurin were, I think, Brits, probably mid-19th century, and discovered some things using infinite series, and their name stuck. Over the years, there have been a lot of mathematics generated to help us do mathematics. For example, before about 1970, there was no such thing as an electronic calculator. And, you know, in math, we have to do arithmetic. And how do you do it if you can't just pull your calculator out? And, you know, there are lots of things they did. But as we made the transition into having calculators available for like a few select millionaires, and then for, you know, the upper class, and eventually filtering down to where everyone that wanted one could afford a calculator. Today they give them away, and basically not graphing calculators, but there's a lot of mathematics generated to help us do the things that were hard to do calculations. That's just an example. Calculation. There are lots of other things. Math is generated to help us do math. And then, you know, once technology advances beyond, like, oh, now we have a better way to do it. Well, most of that stuff, it sort of got discarded. Like, we don't need to do it anymore. But some of it became part of the language, and people found other uses that they had no idea about. And so that part of, even though it was originally created to help us do something that we don't need it for anymore, it became a part of the language, a very useful part. It helped us solve other problems. And so it stayed with us. Taylor-Maclaurin series are like that. They were generated to help us, our forefathers, our grandparents, do arithmetic for complicated functions. Okay? But before calculators showed up, people found so many other fascinating ways to use them that they're now part of the language. I was visiting with a student, it could have been one of you. It was in either one of you or somebody in my afternoon section. And, oh, I know, it was in the afternoon section. And he's a science major. And we were talking about series, and he just said to me, like, oh, we're not going to do Taylor series, like he's heard about them. He hasn't had Calc 2 yet, but from his science classes, physics, most likely, he's heard about Taylor series because they've become a part of the language. Okay, originally invented, and I'm going to introduce it the way maybe it was introduced by Maclaurin and Taylor, these two men in England, as a way to help us do calculations, but that's not our main focus. We're just going to help us understand how to come up with them.
Do people use the Taylor and Maclaurin series when they create calculators?
Yes, when they build the algorithms. Absolutely. All right. So what are they? I'm not going to tell you at first. I'm going to tell you a problem I want us to solve, and we'll solve it, and then we'll identify like what we came up with as a Taylor series or a Maclaurin series. And it turns out that every Maclaurin series is a Taylor series, but not every Taylor series. So Maclaurin is a special case of the Taylor. All right, and there'll be cases similar to things we've seen before. All right, so we have some function. And, to keep with the historical narrative here, it's hard to calculate with. We don't have an electronic calculator. It's like a sine. Like, what in the world would you do for like the sine of, 122 if you didn't have a calculator? Like, we don't know. You just have to give up, maybe. All right. So, Will.
Good job, China.
Yeah, maybe. So maybe I can find a function that gets me really close to f of x, and it's of a nature that it's easy to do arithmetic with. Okay, and what kind of functions like that? Well, polynomials are like that. Right? Polynomials are just adding, subtracting, multiplying, easy. And so what we're going to do is we're going to try to find a polynomial. I'm going to call it p of x. And I'll identify p as a polynomial, and then we'll just use it that way. That approximates. F of x. Now, our function, just think about a sine function. It just oscillates back and forth, -1 to 1. And we know that all polynomials eventually shoot off to infinity, one direction or the other. So we really don't have much hope of being able to do this everywhere for a given polynomial. But, maybe we can start at some point. And then we'll see, how far away from that point can we go and still get values reasonably close to the function. All right, so just to start with, let's try to find a third-degree polynomial. Eventually, we want a power surface. We want to limit it to a certain degree. But we'll start with the third degree. See what we can do. Nothing magic about 3, just an example. All right, so I'm looking for a polynomial. It's third degree. And when I specify the degree, let's put the subscript down. So we know we're not looking for like one that works, an infinite degree. It's a third degree. There are 4 coefficients on the third degree polynomial. There's the constant, there's a1x, a2x squared plus a3x. And what I want to do is choose the a values so that P3 of x is approximately f of x for x values. I'm going to start at 0. Just for a nice concrete example. All right, so we're looking for these 4 constants. That makes this third degree polynomial approximate f of x. Well, there's some like common sense. Suppose f does this, I'm off the screen. So there's f, and here's 0. Well, at the very least, I'm going to need my polynomial and the function to have the same value at where I'm attaching it, right? I mean, if I say, well, let's pick my polynomial to have this value, well, now I can't do what I set out to do automatically. Like I got this big gap between the values. So the very first thing we can do, first, let me say, to find 4 constants, we can establish 4 conditions. And the first one is that we want the function evaluated at 0, sort of arbitrarily choosing 0, to match the polynomial. But we need them to have the same value, right, where we're starting. to make the approximation happen. And if you plug in 0 over here, P3 of 0, the only thing that survives is A0. So in other words, we're looking for 4 constants. We found one of them. A sub 0 has to be the function at 0. 1 down, 3 to go. Okay. Now I can pick 3 more conditions. So let's say I make the polynomial pass through this point, but I make the polynomial look like that. So at 0, they're perfect. They match exactly. But if I get very far away from 0, like, man, approximation is terrible. What condition can I impose that's going to save me from that situation? Well,
The functions need to have the same derivative.
they need to have the same derivative, the same tangent line, right? So that'll get rid of this situation, and look what it does for me. Like now they're the same function very nearly for a wide range. So that's the second condition. Here's the first one. I'll number them as we go. The second one we're going to require, we're building the polynomial. Let's start with it. Be the function's derivative at 0. Well, P3's derivative for any old x is A1 plus 2A2 x plus 3A3. Let's calculate the derivative of our polynomial. Plug in 0. What do we get?
Get A1.
A1. So P primed at 0 is A1, and we've decided that we need that to be the same as this, so we've solved for the second one. The coefficient of x is just going to be the derivative of the function we're trying to approximate, evaluated at 0. 2 down, 2 to go. So third condition. Well, if the function is concave down at 0, the attachment point, I really want the derivative to be concave. I'm sorry, the polynomial to be concave down. Okay. And while the number, the value of a second derivative, and we never really interpreted what that means, like it's not more concave down, but I think we'll just kind of go with the flow. We're going to require the second derivatives to match. That way the concavity will be the same. You know, we got a good thing going here. Make the function match, make the first derivative, so we'll just keep going with it. That will guarantee the same concavity, up or down, whatever it is. And P3's second derivative is 2A2 plus 6A3 x. Plug in 0. And what do we get? 2A2. 2 comes from the derivatives, the conditions. And we need the second derivative at 0 to be f double prime. So let's bring that down and solve for A2. And we see it needs to be 1/2. F double prime is 0. Three down. 1 to go. Now, we don't really know what the third derivative tells us. We never really dug into that. We know first is slope, second one is concavity. But we have a good thing going, making the polynomials derivatives meet the functions. And so we're just going to go with the flow. The fourth and final condition for a third degree is we're going to require that the polynomial's fourth. Remember, when we get above 3 derivatives, we write the number in parentheses. equal the function's fourth derivative. But we're only on the third derivative. So we could use primes, I guess. My mistake. You can use 3 in parentheses. We would all know what you mean. All right, so the third derivative of the polynomial well, right there's the second derivative. We're going to get 6a3. And we need that to be that guy. And therefore, a3 is 1/6. And we're done. Let's write it out. Then we'll pick a function. So our third degree polynomial is the function at 0 plus the derivative at 0 times x plus 1/2 the second derivative at 0 times x squared plus 1/6. Okay. And you can see a pattern there. If I wanted the fourth derivative, what do you think the next term would be if I asked for a fourth degree polynomial? 1/8? Well, there would be f fourth derivative of 0, right? We need to know that. And so let me, just for the fun of it, write in like a over 1. So now I've got 1, 1, 2, 6. You recognize that pattern? Or can you look back and see where the 6 came from? How did we get that 6?
You multiply 2 by 3, so it's factorial.
Yeah, we pulled the 3 down. And then we pulled the 2 down. And then we didn't actually do it because it's 1, but we pulled the 1 down. Right? So Will's right. We're building in a factorial there. And after the first 2 constants, you might have thought, well, the derivative is just going to be the constant. But no, by the third one, that factorial starts to matter. The first 2 factorials are 1, so it didn't matter. But now 2 factorial, got to make it show up, and then 3 factorial. And so I think we could add it. Let's try this for 2 functions, and then we'll generalize a little bit. The first one, f of x equals e to the x. So this one is so easy, we can just write it out, I think. What's the function evaluated at 0? 1. What is the derivative of the function evaluated at 0?
1.
What is the second derivative evaluated at 0? 1.
The function is its own derivative.
Let's write what we recognized before just for the fun of it. And third derivative.
1.
There it is. I asked you to bring your calculators today. I asked you last night in an email, right? So hopefully you've done that. And now let's investigate. This is where you guys have such a big advantage over me. When I took Calc 2, it's like, we do the work. Okay, great. Go to the next. But you can see a visual. As soon as we do it, you can see exactly what we're doing. So I want you to graph f of x and 3. And let's pick a good window here. I think we want our x values. We're attaching it at 0, so we need to go from, let's try -2 to 2. And the y values, like maybe -2 to e squared is let's go to 10, maybe something like that. We'll start there. So graph those and see how good we did. We want our polynomial to look identical to the exponential for a while. We know we've got to give up eventually because the polynomial is shooting off to infinity, and the exponential on the left is 1 to 0. have a polynomial. Yeah, and don't write factorials, just write out the constants, so the coefficients are right above this. Did you not get my email? You can do it on your computer. Ben's doing it on his phone. He's got a graphing calculator. He's got a picture for me. Oh, we're getting close here. You have a picture for me? Beautiful. Have a winner. You almost can't tell there's two curves until you get far enough away. Yeah. So one of those is the exponential, one is the 30-degree polynomial. Tell them apart. Oh yeah, now you see the 30-degree line start. It's got to go to minus infinity. Okay, starting top right. Yeah, what about? A -1. It's like that polynomial is like a craft-seeking missile. It's coming up. It's a 3rd degree, so it's coming up from the bottom, which is terrible. But then it finds the exponential, and then it follows it along for a while, right? And then eventually, we know exponential growth is faster than polynomial. Eventually, the exponential is going to leave it behind. If you've got a graph, let's change it to P4, which is super easy to do. You just need to add the 4th power, and we know what the pattern is. 4 factorial, I'll help you out, is 24. So add that, Emma, and see, can we extend it out a little bit further? If the graph of the function was plot, then our polynomial is like a C. This one comes out of nowhere, finds it, stays with it for a while. Yeah, and now you can hardly tell there's 2 graphs there. One of them is a transcendental function, one of them is a simple little polynomial. But in that graph, it was exactly that. Down in the line direction. Yeah, but you get it beautiful. So for a long time there, you can't tell them apart, okay? And it'll only barely get it start to separate. Of course, eventually the exponential is going to go flying past it. Beautiful. That's such a big graph. I'll show it. So this is what, do you have the 4th term in? Yeah. Okay. This is the P4. And so we did it for a little while. I mean, eventually the exponential's going to leave. And by the way, if you noticed, in Ben's graph, you could really see it. The 3rd degree, it's going to infinity in opposite directions. And since the exponential goes to infinity in the positive, then that's what our polynomial is going to do. We made it do it by picking our coefficients. On the back side, because it's 3rd degree, eventually it's going to like go to minus infinity. When we change it to a 4th degree, now it's going to go to infinity in both directions, right? So now it's going to come down from the top, find the function, stick with it. Actually, all of the values are slightly different. We just can't see the difference on our screen. They're so close. Stays with it for a while as we get this exponential growth, and then it takes off. All right, let's do another one. Are there any questions on this? Everybody get a graph? Let's do the sine function. I'll call it g of x. So, and we'll do the third degree. You'll see why. P sub 3, I need the function evaluated at 0. What's the sign at 0?
0.
0. That's awkward. Plus, the first derivative is cosine. The cosine of 0 is
1.
1. So we get 1. Let's write out all the details, even though may not be necessary yet. The second derivative of sine, what is it?
It's negative sign.
Negative sign. At 0 is
0.
yeah, times 1 over 2 factorial x squared. And the third derivative. Negative cosine, evaluated at 0, minus 1. What a mess I've got. Let me write it up above here so it's clear, especially for anybody watching the video. So P3, 0, I'll show all the work here, plus 1 times x, sort of think of that as 1 factorial, plus 0 over 2 factorial x squared, plus minus 1 over 3 factorial x cubed. And now if we clean that up, we get x minus 1/6 x cubed. Now, graph these functions. Sine and the polynomial x minus 1/6 x cubed. And your window, let's do x, I don't know, let's do a full period, minus pi to pi, 3.14. And the y values, well, we know the sign is always between minus 1 and 1. So let's go minus 2 to 2 so we can see how the polynomial finds it and tracks it for a while. And then gives up. Because it's got to race off. Beautiful. Yeah, so polynomial comes down, trying to find sign, it finds it there. So third degree polynomial, just by choosing coefficients, we can make it look like an exponential curve, and then we can make it look like a sine wave, right? For a while. Eventually the polynomials headed off to infinity. But just by crafting those coefficients, it's like we're artists, and we find these smart coefficients that's going to make my polynomial look like really any shape I want, if I know the function for it. And add another term. What do you think the next term is? Plus or minus? I already wrote it. Yeah, it's going to be an alternating series. And how do we get this 6? Try to remember?
It's 3 factorial.
3 factorial. So what do we need here?
5 factorial.
5 factorial. 120. If you're graphing it, you don't know where your actually, all right. Now we have P5. Now, remember where P3 found it. It found it at the bottom. And subtract with it to the top, right? From basically minus pi over 2 to pi over 2. Now, add this term and see if we can expand it out a little further, where the functions are hard to tell apart. I've never used one of these. It's really popular. Nathan, are you getting a graph? Anybody with a blue calculator? I wonder if you're set on these instead of rating. Yeah, now that's a 5th degree, right? Yeah, so now we can get them over the first hump. The bottom one and the top one, it wraps around that just a little bit before the polynomial takes off. All right, beautiful. Let's add one more term. What do you think it's going to be? Plus or minus?
Minus
1 over
7 factorial.
7 factorial x to the 7 factorial is 5,040 maybe. If you don't know where the factorial button is. Yeah, I think it's 5,000. Look like you got it now. How hard did the whole screen. Beautiful. Yeah. What do you think if we keep adding terms? What do you think we could do? We could make it approximate further and further. And like maybe if we didn't stop at a finite degree and took the power series that we're coming up with, maybe it would converge everywhere. Yeah, that's what the evidence is suggesting. This, yeah. Any questions? Okay. You know, for the sine function, if I would have said find P4, the 4th degree, well, that's not a very good ask, is it? Because there is no 4th degree. The coefficient turned out to be 0, the way we're constructing it. It may not surprise you if we go, let's go to cosine. We're going to get this. We're going to get only even power. So let me write the 4th one out. 1 minus x squared over 2 plus x to the 4th over 4 factorial. Technically, that's a factorial. Obviously, we could calculate derivatives. I'm just asking you to like think about it in comparison to the sign that we just did and see if this doesn't make it reasonable. And go ahead and graph those in cosine. See what you think. See if we did a good job. Now we want one that has 1 for the y-intercept. Beautiful. Smaller one, though, you can see the act. Eventually, the polynomial heads off to infinity. And your graph is consistent with the 4th degree, both shooting up. The 6th degree would both shoot down because it would have a negative slope. There you go. 6 factorial is 720. You could add that guy in. See what that gains you. Interesting graph of the polynomial. It's doing its job for a whole period, right? Minus 5 and high. Yeah, and we could keep adding terms, and polynomial would follow the function further and further. If it really is a polynomial, which means it has finite degree, then eventually it's going to give up and head off to infinity. However, polynomials do. The cosine is going to go to infinity in the same direction, either up or down, because it's an even degree, whereas the sine is going to go opposite. All right, so let's summarize. Are there any questions? All right. So the Taylor series. At x equals 0. Remember, we have to kind of decide where we're going to attach it. We're finding a series for the log function. We wouldn't attach it at 0 because the log is undefined at 0. We need another one. But the Taylor series at x equals 0, which, by the way, that is the Maclaurin. I think I spelled Maclaurin wrong there. Should have an A in there. I told you before that every Maclaurin series is a Taylor series. Well, this is what it is. The Maclaurin series attaches at 0. The Taylor series can attach anywhere. And then, you know what I mean by attach? Then we start building out the polynomial that approximates it as we move away from that point. We haven't done anyone yet. That's not 0. And the good news is, I mean, we'll do it. We'll learn how to do it. But most of the time, our focus is going to be on the Maclaurin series. There's an analog here between power series. We learned you can look at power series at 0, right? Or at A. Well, the Taylor series is a power series at x equals A. The Maclaurin series is a power series at 0. And here's how we're going to do it. We have some function. We're working. We start always with some function. And then the Taylor series, okay, let me, because that's all we talked about, I'll do the Maclaurin series, is an infinite series. Okay, so we're not talking polynomial. I could, in fact, you'll see this in the book, they'll talk about Taylor polynomials. That's what we've been doing, right? We've been going up to the 3rd power or the 4th. But when I talk about the series, it's not a polynomial. We include all of the powers of x, all the positive integers. So series as opposed to polynomial. Here's what it is. It's the summation. N equals 0 to infinity. The nth derivative evaluated at 0 divided by n factorial. X to the n. Doing red. So the coefficients, that's the formula that we used in all of those examples, right? Because we want the function and the polynomial to match on all the derivatives. We had to take derivatives and it built up that factorial as we get to the beyond at least the 2nd term. A 3rd derivative, 4th derivative, there's this factorial building up. And we discovered, you know, to make all of those derivatives match, we need the coefficients to be the nth derivative at 0 divided by n factorial. Okay? So that's the definition. What kind of a series is that? It's a power series. What do we know about power series? Well, we know there are exactly three possibilities. In the last chapter, we talked about power series, and we didn't care where they came from. Like, they could come from this or they could come anywhere, but every power series, there are 3 possibilities. Number 1, converge only at 0. I'm talking about power series at 0, obviously. These are like super boring. They converge everywhere. And when that happens, we said the radius was infinity. Or what's the 3rd possibility? They converge on an interval, minus r to r. Only. Well, yeah. There's a finite value of r. On the exam, actually the morning and afternoon had different classes. The first power series, I think for you it was -3 to 3. One of the classes, And I think the other one was -2 to 2. And possibly at the endpoints. The one on the exam converged at the left-hand endpoint, but not the right-hand. Actually, there were 2 on the test. The second one was, noticed it was a geometric series, made it super easy. You could just use what we know about geometric series. All right. How much time do we have? 1 minute. Let's find out for e to the x, which case we're in, the first, second, or third. Now, if we're in the third case, then between -r and r, our graphs are going to look alike. And then, like, beyond that, who cares? We don't know anything about what happens beyond that. There's no convergence. It's like totally meaningless. So we would really like to land in the middle category. So for e to the x, our series is x to the n over n factorial, starting at 0 and going forever. So let's use the ratio test. That's what we use to find the radius of convergence. We've never done anything else. And there's going to be an absolute x survive when I do the algebra. And then I'm just going to get n factorial over n plus 1 factorial. You see, it's like the super fast version of the ratio test, but it's not complicated. What's that limit?
0.
0 times the absolute value of x, which is
0.
Which is less than 1, and it does not depend on x. The series converges everywhere. And what do you think it converges to for a given x? Those graphs. If I plug in x equals 4, I get the polynomial, 4 to the n over n factorial, n equals 0 to infinity. What's that going to converge to? E to the 4th. Yeah, we're constructing those coefficients to get us the exponential, and it converges everywhere. So those are exactly the same function for all x's. It's true for x equals -3,542. It's true for all x's. Okay? And that is the single most important Maclaurin series of them all. We'll talk about others. We'll do that on Monday. See you then. Have a good weekend. Got baseball games, Ben? Here? No. Got softball? Are you playing? Are you healthy? Yeah, you're despite injury, right?
It's like Sn plus A4. And I knew that Sn equals A1 plus B3.
So you should have told me.
I
I asked for the first 4 terms. There's one of them, but I don't see the others.
Oh.
Okay? Oh, stop the video.